Today's lesson is about colligative properties. And so I'm going to visually show you how boiling point will change upon adding solutes, different types of solutes. So the first what we're going to look at is pure water. We know pure water boils normally at 100 degrees Celsius. And just a reminder, pure water molecules are hydrogen bonded between each other with opposite charges attracting each other. And so you'll shift it accordingly so that that's the case. Now, if I added water, or if I added NaCl, so I'm just going to add one formula unit to this, you'll notice that at that point, there would be the water molecules will clump around the sodium ion and the chloride ion to form what is called a shell of hydration. And so we could demonstrate that by adding more water to see how they will hydrate the sodium chloride or sodium ion, as well as they hydrate the chloride ion. Now, the force of attraction that occurs between the sodium ion and the polar water molecules is called ion dipole forces. And because you're looking at ion dipole forces, which is a fully charged particle ion with a partial charged polar molecule like water, that attraction is stronger than the hydrogen bonding that occurs between water and water. And thus, adding a solute like NaCl will cause the boiling point to go up greater than 100 degrees Celsius. Depending on how much you add of the sodium chloride will determine how much that boiling point will elevate above 100. So now freezing would be very similar in the same idea. However, when you're freezing, you're taking the pure liquid, and you're going to organize those particles to freeze. So here's the liquid. It's pretty disordered. It slides. These particles are sliding past each other in the liquid form. But when you're trying to freeze it, what happens is you're orienting these particles to be more organized, so that the partial charges, opposite charges, are attracting each other. So normally pure water freezes at 0 degrees Celsius. Adding a solute to the water, so if you have the water here, so I'm just putting 3 molecules of the water, and then you add a solute to that, this will cause this to have a difficult time organizing and trying to orient these particles. And so you'd have to depress the temperature in order for these particles to organize themselves again with this added solute. So it's going to be less than 0 degrees Celsius as a result of adding a solute to the solvent, the pure solvent. And it will only depress by a few degrees, but depending on how much you add of the solute, that will make it, that will require your freezing point to depress further and further, just like the boiling point would elevate depending how many solutes, or what solute, as well as how many particles that solute contributes. So there's an idea called von Hoff factor. And the von Hoff factor describes just that how much a solute will affect a solution and its freezing point, boiling point, vapor pressure, and osmotic pressure is dependent on the solute itself, what type of particle it is. If it's an electrolyte, like these ionic compounds, the electrolytes will contribute a certain number of particles when they dissociate in the solvent. Non-electrolytes will not dissociate, so they will oftentimes contribute only 1 particle. So this tells you how much the contribution of the number of particles. And we call that the von Hoff factor. So let's look at sodium chloride. Sodium chloride will contribute 2 particles. Magnesium chloride will contribute 3 particles, theoretically. However, measured-wise, experimentally, it only contributes 2.7 particles. Iron 3 chloride contributes 4, but again, It's experimentally 3.4. But we're going to assume the I measured is the same as the I expected. So we're really going to stick with this chart here, because this factor is going to require much more more considerations and calculations and experimental data to be able to figure out. So we're going to use the expected value from all these particles. In other words, we're assuming these particles will have 100% dissociation, 100% of it, not partial dissociation as you would expect it to be, or as it would be measured to be. So let's go ahead and do some problems. So when I complete these problems, I oftentimes, again, I'm not married to the equation. I'm really looking at my units and the representation of those units. So the first one, it says, is a solution is made by dissolving 18 grams of glucose. So here's my solute, and I like to, in a problem, I like to identify them. And then in 150 grams of water. So here's my solvent. The resulting solution was found to have a boiling point of 100.34 degrees Celsius. Calculate the molecular weight of glucose. So now remember, molecular weight is molar mass, and molar mass is a ratio. It's a ratio of mass divided by moles. So I'm just going to remind myself by putting mass of that substance divided by moles of that substance. That's what molar mass is. And the part of the equation for this freezing or boiling point elevation problem is the molality. How we're going to obtain the molar mass or get parts of that molar mass is through the molality equation, or the molality variable in this equation. So let's look. So this is the change in temperature relative to the pure solvent. So water boils at 100, we know, normally. But now with the solution, the added solute, it now boils at 100.34. So the change in the temperature between the 100 and the 100.34 is 0.34 degrees. Now, because glucose is a covalent compound, its von Hoff factor contribution is just 1. So its I, which is the von Hoff factor, is 1. The Kb constant for water, and again, it's all relative to water, is 0.512. And so what we're solving for is the molality. In solving for the molality, we then get a value that is 0.66. This is solving for molality. And I know what molality is defined as. Molality is defined as the moles of solute, which is glucose, over the kilograms of solvent. And we have the grams of solvent, which we can convert to kilograms quite easily by moving the decimal place over to the left 3 spaces. So this is how much water we have. So we want to figure out the moles of solute from the molality that was given for the solution, given its boiling point elevation. So X, which is your moles of your solute, ends up being 0.0996 moles of glucose. And again, labeling is so important as you're analyzing all of these parts of these units. So now we want molar mass. To find the molar mass, as defined up here, is the mass divided by moles of that substance. And the solute is glucose. The substance we're looking at is glucose. So I'll write that in just to make sure we know and we are guided as far as what we're trying to substitute and find. Okay, so to find the molar mass, I need the mass of the glucose. And if you read the problem again, you'll see that this is the mass that's given of the glucose. So you've given 18 grams of glucose. The moles of the glucose was discovered through the molality. So the molality is 0.0996 moles of glucose. So you divide those two numbers and then you get the molar mass, which is 180 grams per mole for the molar mass of glucose. that was pretty straightforward, okay? So now we go to the next question. By the way, you pause as you see needed as you're going through these problems. Please try these problems on your own as a way to just build your problem-solving skills. So let's go to number 2. Number 2, you're asked to find the kilograms of ethylene glycol, which is this formula, with a molecular weight of 62.1. Ethylene glycol is antifreeze. And you're adding it to 10 liters of water to produce a solution for use in a car's radiator that freezes at below 23 degrees or 23.3 degrees Celsius. It gives us another set of information, which is the density of water. The density of water is 1 gram per milliliters. Now, we know we're going to have to use this equation because it tells you how much it depresses the freezing point as a result of adding ethylene glycol. That prevents your radiator from freezing over really easily. To freeze is to go below 0, but really negative 23, which is really low. So we're using this equation, which is the same as the boiling point, but it now has a different molal freezing point constant, which is 1.86. So the change in temperature, water freezes at 0. If you go below that, or you go below negative 23.3 degrees, the change in temperature is 23.3. The von Hoff factor, because it's a covalent compound, is 1. The Kf is 1.86, and that's given to us, and that's water's constant, freezing point constant. And then the molality is what we're trying to solve for. And so solving this equation, molality, multiplying and dividing, you get 12.4 molal, okay? But now, what is the definition of molality? Molality is defined as the moles of the solute, which is not given to us, over the kilograms of our solvent. Now, so let's take a second look here. If the density is 1 gram per 1 milliliter, as stated right here, of water, if I wanted to interpret that in terms of liters, 1,000, we're proportioning this out really quickly so we can see the relationship. So 1,000 milliliters is 1,000 grams. So notice this ratio is still 1. But now why did we ratio it to 1,000? Well, because 1,000 kilogram is really, or 1,000 grams is 1 kilogram, which means 1,000 milliliters is 1 liter. So this ratio is equivalent in terms of the kilogram to liter relationship. So if I have 10.0 liter, I really have 10.0 kilograms. So I'm going to write that in, of water. And I'm going to label the water just to make sure I know what I'm looking at. This is my solvent. Solving for X, which is the moles of my solute, I get 125 moles of C2H6O2. And then, of course, I'm trying to find the kilograms, which means I'm going to need to use molar mass. So 1 mole of this compound has a mass of 62.1 grams. And then I do an extra conversion to get to kilograms. So 1,000 grams in 1 kilogram gives me a value of 7.78 kilograms of my compound, ethylene glycol. Okay. All right. So we go to example number 3. These problems get a little bit more and more difficult. So be prepared for each one. Okay. So now we go to example number 3. In example number 3, we're looking at finding the normal boiling point. So really we're focused on finding the delta T here of a 2.7 molarity aqueous solution of KBr that has a density, so the solution's density is 1.8. grams per milliliter. So again, identify the solute, and I'll put it over here so that I know. So this is my solute. The solvent is water, so I can just put the word solvent above H2O here. Identifying that will help you to know how you're converting it and where you're going, how you're going about converting it. So to find the change in temperature, we're going to need all of these variables right here. I, the von Hoff factor, assuming that it's the measured and the actual the particles dissociated are the same. The von Hoff factor for KBr is 2 because it breaks up into 2 particles, K plus and Br minus. The Kb is given to us. It's boiling point of water. And then the molality is what is hard here. We need to find the molality. Well, the only information we're given is molarity and the density. So let's go to the side and explore what molality is. Molality, by definition, is moles of KBr over kilograms of water. Now, the problem is molarity is different from molality in the sense that molarity, capital M, is moles of solute, which is KBr, over liters of solution. So the problem is, how do we get these 2 units to match? Okay, so from molarity, or from liters of solution to kilograms of water is how do we do that? And we're going to have to use density for that. So the first thing I want to do is, knowing that the molarity is by definition, molarity is 2.70 moles of KBr over 1 liter of solution. Knowing that information, I'm going to take my liter solution and try to convert to water somehow. So the first thing I want to do is use density. So I'm going to take my 1 liter and try to get to water, of solution to get to water of kilograms somehow. And so I'm going to first do the 1 liter of my solution. I'm going to convert it to grams. That's what I'm trying to do of my solution. So, because I see that there's this density value. So I'm going to do 1 liter, 1,000 milligrams. This is the first conversion. And then I'm going to use density now. I'm going to take the milliliters. For every 1 milliliter, there's 1.80 grams. But I don't want it in grams. I want it in kilograms. So I'm going to take that, and I'm going to take 1,000 grams is 1 kilogram. So that will then give me my kilograms of solution. So I end up with 1.80 kilograms of solution. Now, what is the solution made up of? I know that it's made up of KBr and water. So that reminds me what my solution is comprised of. So now you're going, how do I get in order to get to water, I got to get the KBr out of this, the mass of the KBr out of this. And so we know the moles of the KBr. We can figure out how much mass is in that solution that's contributed by the KBr. So you take the molar mass of KBr, 1 mole of KBr has a mass of 119 grams, and then you convert it to grams to kilograms. This will then give you the kilograms of KBr that's in the solution, in the 2.7 molar solution. So this is the amount of KBr in there. Now, let's think about this logically. If your solution's mass is 1.8 kilograms, and it's both KBr and water, and if your solution also has 0.3213 kilograms of it is KBr, to find the amount of water is just to subtract those two. And in subtracting those two, I get 1.4787 kilograms of water. So now what I could do is I could then, to find my molality, I know there's 2.70 moles of my KBr. And I know that there's 1.4787 kilograms of water. I then can ratio those two out and get my molal. And I get 1.83 when I ratio those two out. And now I can substitute it into this equation and find the change in temperature. The change in temperature, when I add KBr to it, is 101.87 degrees Celsius. Oh, sorry, it ends up being 1.87 degrees Celsius, but adding 100 to that will then give you how much it elevates the boiling point. So again, when you solve this, you'll get 1.87, add 100, because water boils at 100, you'll get 100. So really TB, so technically I should do this. So TB is 100 plus 1.87, and that will give you 101.87 degrees Celsius. Okay. Okay, we're gonna finish this problem up. And so if you look, the change in temperature is 0.307. So let's put 0.307, my apologies. And the I, because it's covalent, is 1. So the von Hoff factor is 1. And the Kf given to you is 0.5, or I keep on putting 0.5 because it's water. But this is benzene. Benzene is the solvent. So 5.12. So again, it's good to identify what your solute is. So my unknown is my solute, and my solvent is benzene. And then molality is what you're trying to find. And when you multiply these and divide, you get the molality to be 0.0600. And again, by definition, molality is the moles of the unknown. So this is my moles of unknown over my kilograms, which is of my solvent, which is 0.500 kilograms. Solving for x equals, in the end, when you solve for x, 0.0300 moles of who? My unknown. And so I'm going to call my unknown CX, HY, and Z. Now, to find the molar mass, I'm going to need the mass and the moles of my unknown. The mass of my unknown is given to be, so right here I'm doing molar mass calculations. Molar mass is mass of my unknown, which is 3.84 grams. Moles of my unknown, which I found through the molality, and this is all CX, HY, and Z, same substance. And as redundant as I am, labeling really does help me to guide myself through the problem. So divide these two numbers and you will get the molar mass to be 128 grams per mole of this compound called CX, HY, and Z. Now, how do we know what the molecular formula? We know what the molar mass of the molecular formula is. We don't know what the molecular formula is unless we compare it to the empirical formula. So we're going to do a ratio between the molecular weight of the molecular formula to the molecular weight of the empirical to see how many times it is. So to do that, I know the molar mass of my molecular formula. It's 128 grams per mole. I know the molecular formula, so I'm going to have to find the molar mass of this formula. And so I take 4 times 12.01 plus 2.02 plus 14.01 gives me a molar mass value of 64.07 grams per mole. And when I ratio these two, I get 2. So it's a multiplier of 2. So my formula is going to be twice the empirical formula. So what is twice that empirical formula? That would make it C8, H4, and N2. Okay, that ends it.